Hello everyone and welcome to Lesson 9, Total Internal Reflection. Our goal for today will be to learn about this process and how it occurs. Just to briefly summarize, what do we already know so far? When light travels from one medium to another, light changes speed, and this is due to a change in the optical density of the two media. And this caused not only a change in speed, but also a change in the direction of the light ray. We'll look at some cases now. Case number 1 occurs whenever light bends towards the normal. In this case, light would enter the new medium with a slower speed, and that's because this new material is more optically dense. This can be seen in the picture below. Say we have an incident ray of light going from air to water. Water is more optically dense than air, which is why as light travels from air to water, it bends towards the normal. Okay, don't forget this dotted line is the normal. In case number 2, light bends away from the normal. Whenever it enters a medium with a faster speed of light. And this occurs when the material that it enters is less optically dense. Similarly, if you look at the picture below, we have an incident ray of light traveling from water to air. We'll label the normal again. And you'll notice that the light ray, after refracting, bends away from the dotted line. In other words, bending away from the normal. Okay, so that's the key thing to take away here. When we go from a more dense to a less optically dense medium, light bends away from the normal and vice versa. This actually leads to an interesting phenomenon. What if, for this second case, whenever light enters a faster medium, what if we were to keep increasing the angle of incidence? Well, recall, light will bend away from the normal, so in all cases, whenever we enter a faster medium, the angle of refraction will always be greater than the angle of incidence. But if you make your original angle of incidence bigger, then that refracted angle will be even bigger than that. So what happens if you keep increasing it? Well, the refracted light ray will keep increasing as well until it reaches 90 degrees. And 90 degrees in this case would be the maximum angle of refraction. So if you keep increasing the angle of incidence, the angle of refraction increases until it reaches 90 degrees. And this occurs at a certain angle of incidence that we call the critical angle. So just to summarize, the critical angle is the angle of incidence that causes the angle of refraction to be 90 degrees. Let's take a look at the picture below. Here we have light going from water to air. Notice that because we're going from a more dense to a less optically dense medium, the light ray will bend away from the normal. So let me just demonstrate this. Imagine if we were to increase the angle of incidence, maybe something like this. Because we're going from a more to a less dense medium, the refracted ray of light will bend away from the normal, like this. And that process will keep occurring until you hit a certain critical angle, which is shown in the picture to the right. And in this case, we have a critical angle of 48.8 degrees. And in this example, this critical angle causes the refracted ray of light to reach an angle of refraction of 90 degrees. And you can see that right here. Look at the 90-degree angle I'm drawing in the picture. So there's a 90-degree angle between the normal and the refracted ray. If you were to further increase the angle of incidence, the refracted ray of light wouldn't go past 90 degrees. So it turns out in water, the critical angle is this 48.8 degrees. And you can imagine every medium will have its own critical angle. Let's take a look at the picture below, and there's one thing to note. If light travels slower in a particular medium, the critical angle will be smaller. So notice we have three examples here: water, glass, and diamond. That would be our medium number 1. And we're going to air, which would be medium 2. Don't forget the dotted line represents the normal. Now it turns out that light will travel faster in water than it does in glass, and light travels faster in glass than it does in diamond. So what we're showing in this picture is the slower that light travels in a particular medium, the smaller the critical angle will be. So for example, if going from water to air, there was a critical angle of 48.8 degrees, which is the angle that causes the refracted ray of light to enter the second medium at an angle of 90 degrees, then because light travels slower in diamond, it's going to have a much smaller critical angle, in this case 24.4 degrees. And the reason for this, light refracts or bends more when it goes from a very slow medium to a faster medium. Okay, so something interesting happens if we further increase the angle of incidence. If you increase the angle of incidence past the critical angle, we get a unique phenomenon occurring, which is total internal reflection. And let's discuss what this phenomenon is. When our angle of incidence is larger than the critical angle, all of the light rays are reflected back into the first medium. No light rays are refracted out. Please note this will only occur when light travels into a less optically dense material where the light will move faster than it did before. So let's sketch it out. Let's say this is our interface between air and glass. I'll sketch a normal. And we'll look at a few examples. Let's say we had some incident ray of light shown below. Because we're going into a less optically dense material, light will bend away from the normal. Imagine now we had a second ray of light at a slightly larger angle of incidence, but imagine that it was exactly at the critical angle. So here's our incident ray of light. If that occurs at the critical angle, then the angle of refraction will be 90 degrees. And finally, if you increase that angle of incidence, the light isn't going to refract any further. It can't refract past 90 degrees. Now, so far we've only been talking about refraction, but you actually get reflection occurring at the surface as well. So please don't forget when we were looking at plane mirrors, we said that plane mirrors obey the law of reflection. That is, the angle of incidence equals the angle of reflection. So when you're past the critical angle, you're just going to see reflection occurring, no refraction. And this is the phenomenon of total internal reflection. At a certain range of angles, you get all of the light staying on one side of the material. Okay, and we can see this in the picture below as well. So let's summarize what are the conditions in order for total internal reflection to occur. First of all, it only happens whenever light travels from a slower medium into a faster one. And this occurs when the angle of incidence is larger than the critical angle for that material. So with that being said, we're now going to look at some applications of total internal reflection. One example are with diamonds. The reason why diamonds are so attractive is because they sparkle. And believe it or not, this is done intentionally. This is due to the cut of the diamond faces, and in addition, diamond does have a high index of refraction. This results in a small critical angle. And these two factors cause light to undergo total internal reflection in a diamond. When a light ray enters a diamond, it'll reflect off of the various faces, and it'll do this several times before escaping, and this is what causes that sparkling effect. As we'll see in the picture below, this is dependent on the cut of the diamond. So look at the picture to the left. If the diamond is cut too deep, then the light rays are going to escape quickly. On the other hand, if the diamond is cut too shallow, once again the light ray escapes very quickly. But for an ideal cut, let's take a look at what happens. You have some random incoming incident ray of light. In this case, we're going from air to diamond. When light enters that diamond, it'll reflect off of the various surfaces. Okay, and it's the fact that light is bouncing around in the diamond which is giving it that sparkling effect. So that's one application of total internal reflection. We'll look at another one, and this has to do with fiber optics. So you may be familiar with this, but it's a technology that uses light to transmit information along a glass cable. All right, and modern telecommunications uses fiber optics to send information all over the planet. Because that light carries information, it must not escape as it travels down the cable. The cable itself must have a small critical angle, and this will ensure that the light entering will have an angle of incidence that's greater than the critical angle. This causes total internal reflection to occur within the fiber optic cable. And that's how we get this beam of light to travel. Okay, so as I mentioned before, fiber optics are used in modern telecommunications. And this helps our various devices such as phones, computers, and TVs to send and receive information. Similarly, the automotive industry will use fiber optics in order to transmit light to the instrument panel in cars. We also see uses of it in the medical profession. So doctors will use fiber optic technologies to look into parts of the human body. They'll use something called an endoscope to check on the health of various organs. So doctors will use fiber optics to help them diagnose. The endoscope itself consists of two fiber optic bundles. One of those bundles will shine light into the body, and the second bundle carries the reflected ray of light back to the instrument. Alright, and that's going to wrap up lesson number 9. Thanks for watching, everyone. We'll see you in the next video.